Sorry about that, folks. Technology is technology. We'll pick up from right here. Okay, so um, estimating the p-value of a t-test. So this is a left-tailed test. N equals 2 and t equals negative 1.938. So think about what this is. We have our t-curve. And negative 1.938 is right here. And since it's a left-tailed test, we're wanting the area to the left here. Okay. N equals 12 means your degrees of freedom is 11. N minus 1. Okay. So flip to your appendix and look at table 4 in your appendix. And if you're looking at table 4, none of those numbers in there equal negative 1.938. None of them are even negative. Why are they not negative? Well, if you'll look in the top left-hand corner, you'll see the graph of the normal t-curve. And notice it's shaded to the right. So all of those numbers are based on the positive side to the right. So since this graph is symmetric, if we figure out what 1.938 to the right, if we find that area, it will be equal to the area of negative 1.938 to the left. So take your degrees of freedom, it's 11, go down to row 11, and find 1.938. And the first thing you're going to tell me is, Mr. Francis, 1.938 is not there. And you are correct. But these two are. And 1.938 is directly in the middle of 1.796 and 2.201. It's in between there somewhere. Okay? So, if we portray that to the left, then what we say is this. The area... the area under the t-curve to the right here, this area here, the area under the t-curve to the right is between 0.05 and 0.025. It's in here. That's the area. Is in between there. Now notice with your table up at the top, your t sub alphas, 0.10, 0.05, they get smaller as you go to the right. So that's why 0.05 is on the left with this particular picture. Okay? So this would be correct there. So your area is between those two values. So if we flip it to this left-hand side, we can say the same thing about it. It's between those two values. Now, when you start thinking in terms of p-value, p-value is basically a probability of the significance against the significance level. So what we can actually say is this, for this left-hand side here, is that our p-value is between 0.025 and 0.05. 0.025 and 0.05. So we don't know what the p-value is. You would need something besides the table. The table just doesn't give you enough data to find that p-value. But you know a range of the p-value. It's between those two numbers. Okay? So what does that tell us if we know the p-value is between these two numbers? Well, it tells us this. It tells us that if our significance level is greater than or equal to 0.05, so if it's 0.05 or larger, we can reject the null. We can reject the null. Now, why do we say that? Because think about it. Look at the range that our p-value is. What does our definition say? If p is less than or equal to alpha, we can reject. That's what our definition says. So if alpha is greater than our largest possible p-value, then no matter what the p-value is in here, it's going to be smaller than alpha, so we can reject it. If alpha is less than or equal to 0.025, we cannot reject. Now think about what that means. If alpha is less than our smallest value that p could be, then that means p will be greater than alpha no matter what it is. So that would make sure that we could not reject our null. Does that make sense? Hopefully so. All right, so the question of the day, though, is what about between 0.025 and 0.05? Because not every number between there is the p-value. There's only one p-value for each t distribution, right? Only one p-value. So what about between there? Well, the only way to figure out between here is with statistical software. The table just does not give us enough data. So what we would say is this, is if the significance level is between here somewhere, of course it's not the p-value, but if it's between here, what we say is cannot decide. Okay, we cannot decide based on the table. It's just not enough information. It doesn't sufficiently provide us with the information we need to be able to solve it. Okay? Alright, so that's letter A. Let me erase this and come back. And we'll do letter B. Alright, so for letter B, it's a two-tailed test. Okay? And N is 25, T is negative 0.895. So think of your T-curve. And we know that this is 0.895. And since it's two-tailed, we know it would be to the left of this, but we also know we have something to the right over here because it's two-tailed. That would be 0.895, the positive version. And we know the degrees of freedom here is 24. 25 minus 1. Alright, so go to the back of the book, and what you've got to think of here, we're not going to be able to find the area to the left, the negative 0.895, in Table 4. Remember, it only gives us the positive values, and it's only to the right, if you remember. It's not area to the left, it's area to the right in the T table back there, the Table 4. So what you have to do is you have to find this area, this value, in your T table. And whatever that area happens to be, whatever that value happens to be, will be the same as the area on the other side, okay? Whatever that value happens to be, it will be the same on the other side since they're symmetrical. All right, so let's go to the back and let's look at Table 4 for 0.895. Well, first of all, go to the degree of freedom 24. 0.895. Now, if you notice, 0.895 is smaller than any other value in that row. In row 24, 0.895 is not in there. It's smaller than any other value in that row. T is 0.10, which equals 1.318. This is the smallest value in that particular row. And 0.895 is even smaller than that. Okay? So, what do we have to do here? Well, what we have to do is this. The area under the t-curve that lies to the right of 0.895, the area to the right, is going to be greater than 0.10. Because remember, look at the table again. Look up at the top. We're getting 0.10 from our alpha up there at the top, very top row. As you go right, our alpha gets smaller, 0.05, 0.025, so on. But since this value is smaller than any other thing, we're going left. So that means we get larger, okay, as we go left. So that means this 0.10, our alpha has to be larger than 0.10. So that means our area under the curve that lies to the right of 0.85 has to be, the area has to be greater than 0.10. Okay? For that right there. The area has to be greater than 0.10. So, what does that mean? Well, this is a two-tailed test. So remember how we do this p-value. We have to take these two p-values in common. So what we actually have right now for this one side right here, this one side, p has to be greater than 0.10. Our p-value has to be greater than 0.10. But we have two equal sides to this. One right here as well. So what that means is p has to be greater than 2 times 0.10. So p has to be greater than 0.20. 2/10. Okay? P has to be greater than 2/10. So this is what we would say. The area under the t-curve that lies either to the left of negative 0.895 or to the right, because it's two, it either lies to the left of this or to the right of this, is greater than 0.20. So P has to be greater than 0.20. So here's what we say. If alpha, if alpha is less than or equal to 0.20, if alpha is less than or equal to 0.20, that means our p-value will be greater than any alpha we can have. So that would mean that our alpha, if it's greater, we cannot reject. That would mean we cannot reject the null hypothesis. Now remember, alpha is our significance level. So if our significance level is less than or equal to 0.20, then that means our p-value here is going to be greater than any of our significance level, and so we cannot reject. However, for significant levels that are larger, suppose it's larger than 0.20. Suppose it's larger than 0.20. Well, because here's the deal. We only have one p-value in this interval. Okay? There's only one p-value in here. So if the p-value could be at 0.8, well, everything up to 0.8 could be an alpha, or everything on the other side of 0.8 could be an alpha. So we don't know. It gets real vague because this is an infinite interval here. So we don't know what the alpha could be here. We could decide on the other one because it would be less than this interval no matter what we selected. No matter what this alpha was, it would be less than this interval. That's why we cannot reject. But as far as this, it might be less than P, it might not. It just depends what P is. Because of that, we cannot decide. Okay? Table 4 doesn't give us enough information to make a competent decision, so it's not sufficient enough. You would need some kind of statistical software to be able to decide that. Okay? Alright, so now we do have a step-by-step guide for doing a t-test. This is finding the p-values of it, and I know that's a lot to think of. But here is the actual procedure for finding a one-mean t-test. Notice we do the null, significance level, instead of the z, on the test statistic, instead of the z-score, we're doing the t-distribution. Okay, looks very much like our z-test up to this point. It even looks very much like our z-test here, because we have a critical value approach, we have a p-value approach. Okay, so I'm going to show you the critical value approach just because I believe it's a little more simple for you to do here. The p-value approach is shown in your book, and you're welcome to look at it and try to decide p-values. One reason I don't show the p-value approach very much, you may have a few p-value problems for homework, just to get you familiar with it and let you kind of do a little discovery learning on your own, ask questions of your instructor, kind of stretch your mind so that you can think about the p-value approach. But mostly you'll see a lot of critical value questions because p-value, as we said, sometimes you don't know what that is. Most of the time you don't know what that is, so you have to you cannot decide on certain parts of it. The critical value approach, we don't run into that problem, and I'll show you why here in just a moment. Alright, so here's our problem. Acid rain from the burning of fossil fuels has caused many of the lakes around the world to become acidic. The biology in these lakes often collapses because of the rapid and unfavorable changes in water chemistry. A lake is classified as non-acidic if it has a pH greater than 6. If it has a pH greater than 6, it's classified as non-acidic. Marchetto and Lamy measured the pH of High Mountains Lake in the Southern Alps and reported their findings in this magazine. Table 9.12 shows the pH level. Shows the pH levels attained by the researchers for 15 lakes at the 5% significance level. Do the data provide sufficient evidence to conclude that on average, High Mountains lakes in the Southern Alps are non-acidic? Non-acidic. Alright, so lakes are acidic. When we get ready to find our null hypothesis and our null hypothesis and our alternative. So what would the null hypothesis be here? Well, if it's equal to 6, we say it's acidic. The alternative, which we're testing here, okay, is if our mean is greater than 6, because greater than 6 would mean that it's non-acidic. Okay? Would mean that it's non-acidic. So what this tells me automatically, the one thing I see, is that it's right-tailed automatically. So there's my hypothesis. Now, before we get started, let's do a normal probability plot. Hopefully you're getting used to those now so that you can do them either in your calculator. Remember, I showed you how to do those in your calculator. Hopefully you're using your calculator to help you with those. If not, you can. I showed you the old-fashioned way as well, and you can use that. This would be a good chance for you to do it. And if you the normal probability plot for this particular problem is at the bottom of page 375 if you want to look at it. And notice what it says. And you can double check yours when you do your normal probability plot against this. Okay? Against this one. So no, it's linear, no outliers. So everything's good to go. So we can apply this t-test. Okay? Notice we didn't have a standard deviation in there. That's the one thing that clicks in my mind that we're going to do a t-test. Okay? So first things first, what is the significance level? That was given to us in the problem. The significance level is 5% or 0.05. Okay? Now we've got to compute our test statistic, which this is our test statistic right here. Okay, so we know the population, which is 6. 6 has to be our population mean here. We also know that there are 15 values, so we know n. The two things you're going to have to find for this problem is you're going to have to find the sample mean and the sample standard deviation. So take the data that you see here in the table, add it all up, divide by 15. That's going to give you your sample mean, which turns out to be 6.6. And also take this and put it in the computing formula, or if you've got a calculator that will do it for you, to be fine, and find the standard deviation. Okay, and that will be your if you do it correctly, 0.672. This will be a good chance for you to practice standard deviation for the final exam. Sample standard deviation. Review that computing formula, remember. And this gives you 3.458. Alright, so that's our test statistic. Now we're going to use the critical value approach instead of the p-value approach. Alright, so for the critical value approach, what we have is this. Okay? The critical value for a right-tailed test is t sub alpha with a degree of freedom of n minus 1. Okay? So our alpha is 0.05, and our degrees of freedom is going to be 14. 15 minus 1. Okay? So what we need to do is go back here to table 4. Okay? So flip to table 4 in the back of your book. Go down your column to 14, where the degree of freedom is 14. Go over to 0.05. And you should see there that is 1.761. 1.761. Alright, so for critical value, remember this is what it means. Here's our t-curve. You have 1.761 is that critical value. Okay? And it's right-tailed, so that means this area to the right is the rejection area. This is where, for critical value, because it's right-tailed, if it was left-tailed, the area to the left would be the rejection area. Okay? And this is the non-rejection area. Non-rejection area. Okay? So, what you need to do is look at your value for t. Where does it fall? Okay? Our value for t, the observed value, is 3.458. Well, that's going to fall over in here. 3.458 will fall somewhere over in here. So notice that is in the rejection area. So, since it falls into the rejection area, we reject the null. So what this means is that these test results are statistically significant at the 5% level. These test results are statistically significant at the 5% level. Alright, so now, what about that p-value approach? I know I told you I wasn't going to show you that, but I hate leaving here without you seeing it. So remember, our test statistic came out to 3.458. Our alpha is 0.05. Okay? So, what we need to do is go back to our table in the back of our book, our table 4, and we have a degree of freedom of 14. A degree of freedom of 14. So go scroll down the page to 14 and look for 3.48 in that row. Well, 3.48 is larger than any of the values in that row. So look up at the top. That's 0.005. Notice, remember what I said, our alpha values as we go to the right get smaller. So what we would say is that our p-value has to be less than 0.005. The p-value has to be less because this number is larger than any number in that row, so we would have to continue going to the right. And as you continue going to the right, that means that alpha number is going to continue to get smaller. Thus, our p has to be less than 0.005. And if you used technology, the actual p-value here would be this. So if you want to use your calculator to try to figure out what it is, you can use it that way. But normally, you wouldn't be able to figure that out. So p has to be less than 0.005. Well, our significance level is 0.05. So no matter what p is in this interval, this is the highest p could be. It's going to be less than that. So because of that, that will always be less than alpha. That's always going to be less than alpha. So we reject the null. Now we found that out anyway with our critical value approach. So the test results are statistically significant. So that would be the way you would solve it using the p-value approach. It's just a little, the critical value approach is a little more cut and dry, where the p-value approach is kind of abstract. So it just depends how your brain functions, whichever one you want to use, unless it asks for one or the other. If it doesn't ask, if it just tells you to solve it, go for it. So use whichever one you want. So hopefully that made more sense to you. Hopefully this is going to help you. Have a great day and contact your instructor if you have any